Okay. Like be 30 minutes then, that'll be okay for you.
Okay. Finish him. Kill the guy now. Grab the gun. Hit him.
What? What is this?
Good day, sir.
You are watching Jackie Pan in my house.
No, it's King Kong, sir.
King Kong. You've never heard of ACTV before in your life? ACTV is very educative, informative, and there are football sport there. There is entertainment. There are a lot of things you can even attend lectures here. All you know is watch all those nonsense artists and do nonsense, or you watch nonsense on TV. Last night you almost came in bed with your fist.
It's not me, sir.
And you wake up every morning, the bed will be so rough, like you've been fighting for food in your dream. That's the reason why you have F's in your courses, like especially made for you.
I have you last semester.
We eat by pounds on you. Very stupid. Oh, yeah, change that section to ACTV right now. And oh God, the baby was what the first born. Stupid boy.
Yeah, good afternoon, students. You are welcome back to another section of this class, CHE 214, Nuclear Chemistry. Yeah, last time we met, we discussed about the calculation of kinetic chemistry. So today, we will be looking at a different topic, which is the group displacement law. That is what we'll be looking at today. And I'm sure as you go along with me, you have one or two things to gain from this. Happy view. Yeah, when we talk about the group displacement law, this will take us back to the periodic table. Elements in the periodic table are arranged in order of increasing atomic number. When you look at the periodic table very well, from the hydrogen, which is the first element, to the last element, you see that from the left to the right, as the atomic number is increasing from one period to the other. That means as these elements are arranged in the periodic table, from the first one to the second one, the atomic number are as well increasing. So the position number of each of the elements corresponds to its atomic number. The position of each element in the periodic table corresponds to the atomic number of that particular element. When you look at oxygen, the position of oxygen in the periodic table corresponds to the atomic number of that oxygen. And the atomic number of oxygen is 8. When you look at sodium, the position of sodium in the periodic table, which belongs to group 1, its position corresponds to the atomic number of sodium, which is 11. So the position of all these elements in the periodic table correspond to the atomic number of that particular element. If the atomic number of a given element is changed, definitely the group will also change. When you change the position of a particular element, for instance, let's look at sodium. Sodium is in group 1. It's in group 1. It's in the first group. Because the last valence, the only valence electron, the unpaired electron of sodium is 1. So sodium belongs to group 1. So, and the atomic number is 11. When you change the position of this sodium, maybe you change it, this is group 2, for instance, group 3, group 4, group 5, and so on and so forth. When you change the position of sodium, probably to this, to group 3, definitely the atomic number of that sodium will change. The group to which that sodium belongs to will change. So the position of a particular element is determined by the atomic number of that particular element. As we already know that, if an element undergo alpha emission, the atomic number will decrease by 2. And if it undergo beta emission, the atomic number will increase by 1. When it undergo alpha, the atomic number decreases by 2. When it undergo beta, the atomic number increases by 1. Let's look at the illustration of group displacement element. The illustration of a group displacement element, let's assume we have group 4B, we have group 5B, we have group 6B. Under this group 4B, we have an element there. Under this group 5, we have uranium there. Under this group 4, we have another element there. So this element is referred to as thorium. The element TH is referred to as thorium. The element U is referred to as uranium, while the element PA, is referred to as protactinium. Now, when an element undergo an alpha emission, that is uranium, and thorium undergo a beta emission, this is uranium, is undergoing an alpha emission. The atomic number of that uranium will decrease by 2. This means that the position of uranium will shift to the left 2 times, 2 places on the periodic table. The position will shift to the left 2 places on the periodic table. When thorium undergo beta emission, the position of thorium will shift to the right once on the periodic table. Simply because alpha emission, the atomic number will decrease by 2. Beta emission, the atomic number will increase by 1. So we can see uranium here. Uranium shifted. It did not stay in the position of group 5B. It moves to 4B because the atomic number has decreased by 1 and by 2. Thorium shifted once to the right simply because the atomic number has increased by 1. So that is the illustration of group displacement element. Now let's see what this law says. The group displacement law states that in an alpha emission, the parent element will be displaced to a group 2 places to the left, and in beta emission, it will displace to a group 1 place to the right. It undergo alpha, it displaces 2 groups to the left. When it undergoes beta, it displaces 1 group to the right. That is what this law states. That is the group displacement law. Now, under this, we are going to look at some calculations here that we have to do with alpha and beta. The first question is this. The mass number and atomic number of a radioactive. The mass number and atomic number of a radioactive. Of a radioactive elements. Elements actinium. are 227 and then 89 respectively. Calculate the number of alpha and beta. The number of alpha and beta particles emitted if the mass number and if the mass number and the atomic number of the new element lead, which is Pb, are 207 and then 82 respectively. Yeah, here we are to calculate the number of alpha and beta emitted if the mass number and the atomic number of the new element lead are 207 and 82 respectively. The element given is called actinium, having mass number 227 and atomic number 89. This element undergo a radioactive decay, and another new element is produced, which is lead, having mass number 207 and 82. The number of alpha and beta emitted, is what we are to calculate here. Now let's quickly run through this. Solution. Let's look at the reaction. We have 227 and then 89. That is for actinium. Actinium is bombarded to produce lead, which is Pb, having mass number 207 and atomic number 82. Then is subjected to alpha and beta, alpha 4,2, which is helium particle, and plus beta, which is a 0 minus 1 electron. So now we want to know the number of alpha particle and the number of beta particle emitted. So this we pick our first equation here. We are going to have about 2 equations. So the first one, 227, that is for the mass number of actinium, is equal to 207 mass number of lead. Then plus 4 alpha. This is our alpha. 4 alpha plus how many beta do we have there? We have 0 beta. We are dealing with the mass number now. You first deal with the mass number, then you deal with the atomic number. Then plus 0 beta. So this will give us 227, which is equal to 207 plus 4 alpha. Rearranging this equation, 207 plus 4 alpha is equal to 227. So our 4 alpha, collecting the like terms, is equal to 227 plus 207. So 4 alpha is equal to, if we subtract this, we are having 20 there. So alpha is equal to 20 divided by 4. So our alpha is equal to 5 there. So that's the number of alpha emitted there. So to calculate the number of beta emitted there, we make use of the atomic number. And the atomic number here is 89. So 89, to calculate beta, 89 is equal to 82 plus 2 alpha plus minus 1 beta. So 89 is equal to 82 plus 2 alpha plus, we have a minus 1 beta. So that's going to be minus a beta. Don't forget, we know our alpha already to be 5, where alpha equals 5. So therefore we have 89 is equal to, we have 89 is equal to 82 plus alpha is 5. So 2 bracket 5, then minus a beta. Plus times minus is minus. So that plus is no more there. So we have 89 to be equal to 82. 89 is equal to 82 plus, this is going to be 10, plus 10, then minus beta. Now, 89 is equal to 82 plus 10, that's 92 plus, minus beta. So 89 is equal to 82 plus 10, that is 92, then minus beta. Rearranging this equation now, we have 92 minus beta is equal to 89. So we have 92, 89 will come, minus 89 is equal to, minus beta will come here to become plus beta. So if you subtract 92 minus 89, you are having 3 there. 92 minus 89. So you're having 3 is equal to beta. So our beta is equal to 3. So that means the number of alpha emitted is 5. The number of alpha emitted is 5. And the number of beta emitted is 3. So alpha is equal to 5, and then beta is equal to 3. Another question, calculate the mass number. The mass number and atomic number of, calculate the mass number, atomic number, and group in the periodic table. In the periodic table for an element bismuth, Bi, in the following disintegration series. Yeah, here we are calculating the mass number, the atomic number, and the group to which this element belongs to. In this, we have Ra to give us Rn. From Rn, we have Po. From Po, we have Pb. From Pb, we have a Bi. So this an alpha, this alpha, This is also alpha, while this is beta emission. RA is equal to mass number is equal to 226. Atomic number is equal to 88. Group number is equal to group 2A. Now, in approaching this, from the instructions we have been given, let's look at the equation. That is the reaction. 226, 89. That is for PA. To give us of helium, to give us of electron, which is equal to A Z of Bi. Now, if we compare this reaction with this series, then we have this. Comparing the mass number 226 minus 3 bracket 4. We are comparing the mass number now for radium. 226, the mass number, 3 bracket 4. That's 3 multiplied by this 4. This 3 is owned by both the mass number of this helium and the atomic number of this helium. So minus 0 is equal to A. That is 226, 3 bracket 4, 0, then is equal to A, which is the mass number there. So we have 226 minus 12. 0 will have gone, is equal to A. So 226 minus 12 is giving me 214 is equal to A. So A is equal to 214. Now comparing the atomic number, this is the atomic number here now. The atomic number is 88. So we have 88 minus 3 bracket 2. 3 bracket 2. Then minus 1. Minus 3 bracket 2. Minus 1 is equal to Z. So that will give me 88 minus 6 plus 1 is equal to Z. 88 minus 6 plus 1. That's 88 minus 5 is equal to Z. So that's 83 equals Z. So there, my Z is equal to 83. Now, we've succeeded in calculating both the mass number and the atomic number of these bit modes. So it means bit modes, this Bi, have mass number and the atomic number. So the mass number is 214 and the atomic number is 83 for that bit mode. And bit mode belongs to group 5A. So bit mode belongs to group 5A. Yeah. So that is it about that. Let me see, maybe we can quickly rush over this before the time is up. So that's number 3. Calculate the number of alpha and beta particles. The number of alpha and beta particles emitted in passing down from 232 thorium 90 to 208 82 PB lead. So we move from thorium to lead. And we have to calculate the number of alpha and beta particle emitted. Well, we move from thorium to lead in the periodic table. Now, the first thing here, first learn how to write out the reaction. The reaction, we have 232, 90. That's for thorium. And we move from there to lead, which is Pb. And Pb is having a 208 and then 82. So alpha and beta particles are emitted there, plus alpha. Alpha is helium particle, as we know, He, and plus beta. And beta is electron particle, which is O-1 electron. So we have to calculate the number of alpha and beta particles emitted here. Yeah. Comparing the mass number, then for the beta, you compare the atomic number. So comparing the mass number, that is 232 is equal to 208 plus 4 alpha plus 0 beta. That's 232 plus 208, then plus 4 alpha. This is equal to, so rearranging this equation, 208 plus 4 alpha is equal to 232. 4 alpha is equal to 232 minus 208. 4 alpha is equal to, if we subtract this from this, what is it giving us? We subtract that, is giving us 24. So my alpha is equal to 24 divided by 4. So alpha is equal to 6. So the number of alpha emitted there is 6. So comparing the atomic number, atomic number. The atomic number are 90 is equal to 82. 90 is equal to 82 plus 2 alpha minus beta. That's minus beta there. Don't forget, where alpha is equal to 6. So you substitute that. 90 is equal to 82 plus 2 bracket 6 minus beta. 90 is equal to 82 plus 12 minus beta. 90 is equal to 82 plus 12. That will be 94 minus beta. 94 minus beta is equal to 90. 94 minus 90 is equal to beta. 4 is equal to beta. Beta is equal to 4. Therefore, alpha equals 6 and then beta equals 4. So we get our beta to be 4 there. Yeah. We still have about 2, 3, 4 questions to solve under this, but I think this is a convenient place for us to stop for today. So I'm sure when you go through this, if you have any question, you send it across to me through my email, and these questions will be displayed on your WhatsApp platform. So you go through them and let me see your reaction. Thanks very much.
Okay.
Finish him. Kill the guy now. Grab the gun. Hit him.
What?
What is this? Good day, sir.
You are watching Jackie Pan in my house.
No, it's King Kong, sir.
King Kong. You've never heard of ACTV before in your life? ACTV is very educative, informative, and there are football sport there. There is entertainment. There are a lot of things you can even attend lectures here. All you know is watch all those nonsense artists and do nonsense, or you watch nonsense on TV. Last night you almost came in bed with your fist.
It's not me, sir.
And you wake up every morning, the bed will be so rough, like you've been fighting kung fu in your dream. That's the reason why you have F's in your courses, like especially made for you.
I have you last semester.
We by pounds on you. Very stupid though. We are changing that section to ACTV right now. And oh God, the baby wants to have the first born. Stupid boy.